This video is about a particular kind of universal gravitation problem with three objects. In general, we have three masses lined in a row, and let's say, for example, this is the mass of 4 kilograms, and this is a mass of 3 kilograms, and this is a mass of 2 kilograms. And the question usually reads something like, find the force on one of the masses due to the other two masses. So what we'll do now is we'll just say, let's find the force on the 2 kilogram mass in the middle caused by the other two. So the first thing we do is determine what the force is by each of the individual objects is on the 2 kilogram mass. So draw a free body diagram of the 2 kilogram mass, and the 4 kilogram mass attracts the 2 kilogram mass, and we'll draw that as the force of 4 on 2. And the 3 kilogram mass also attracts the 2 kilogram mass, so we'll draw that as the force of the 3 kilogram mass on the 2 kilogram mass. So the net force on the 2 kilogram mass is going to be the vector sum of the force by the 4 kilogram mass on the 2 plus the force of the 3 kilogram mass on the 2 kilogram mass. Since these two are in opposite directions, we're going to have to subtract the magnitudes. So basically the magnitude of the net force is the magnitude of the force by the 4 on the 2 minus the force by the 3 on the 2. Because the 4 is a larger mass, I'm pretty sure that the magnitude of the force by the 4 on the 2 is going to be greater than the force by the 3 on the 2, and so therefore I'm pretty sure my net force is going to be positive in magnitude. And since I know that the force of the 4 on the 2 is directed to the left, I know that my net force is going to be to the left. So first, let's find the force of the 4 kilogram mass on the 2 kilogram mass. Force of 4 on 2. That's going to be the universal gravitational constant times the mass of the 4 times the mass of the 2 divided by the distance of separation squared. Oh, haven't decided on any distances of separation. Well, let's see. Let's say this distance right here is 50 centimeters, and this distance right here is also 50 centimeters. So the 2 kilogram is halfway in between the 4 and the 3. Therefore, the force by the 4 on the 2 is big G, 6.67 times 10 to the negative 11th kilograms, times mass of 4 kilograms, times the mass of the 2 kilogram, 2 kilograms, divided by the mass, or divided by the distance of separation squared. And since force is in newtons, and newtons is kilogram meters per second squared, I need to put the distance in meters. So that means 0.500 meters. And then we take out our calculator, and we find that the value here is 2.13 times 10 to the negative 9th newtons. And then we do a similar calculation, only this time for the force of the 3 on the 2. So that's going to be G times the mass of the 3 kilogram times the mass of the 2 kilogram divided by the distance between the 3 and the 2 squared. So plugging in the numbers, that's 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. I notice I wrote something wrong up here. This should be Newton meters squared per kilogram squared also, times 3 kilograms. That's 3 kilograms. Let me make that look a little bit nicer. 3 kilograms times 2 kilograms divided by the distance between them squared, 0.50 meters squared. And for that, we get 1.6 times 10 to the negative 9th. Now, in order to get the net force, we must subtract the two forces. So therefore, let's do this in a slightly different color. the net force is going to be the force by the 4 on 2 magnitude minus the force by the 3 on the 2, that magnitude. So that's 2.13 times 10 to the negative ninth minus 1.6 times 10 to the negative ninth, which is equal to 0.53 times 10 to the negative ninth newtons. So that means the force by the net force on the 2 kilogram mass by the 4 and the 3 combined is 0.53 times 10 to the negative ninth newtons. So just recapping what we've done, we have 3 masses in a row, 4, 2, and 3 kilograms, and we want to find the net force on the 2 kilogram mass, and so therefore we find the force by the 4 on the 2 and the force by the 3 on the 2. We find each of those magnitudes, and once we have found those 2 magnitudes, we subtract them because they're in opposite directions, and we come up with a net force direction to the left of 0.53 times 10 to the negative ninth newtons on our 2 kilogram mass.